I made a mistake last Tuesday. Thanks for letting me know that. I didn't follow properly the order in which the slides were supposed to be discussed and presented. I forgot that before going to the introduction to QoS, we should have looked a little bit at some coding techniques and some application taxonomy, which will motivate the reason why we are going to describe the traffic characterization in terms of point of service. However, the mistake was not so big because we just discussed the first slide in that set of slides. So, and that introduction doesn't need this part, but keep going would be a little bit a problem. So we will start now with discussing a little bit about coding techniques with particular reference to voice, video, and audio, and then a kind of application taxonomy, application description to highlight some issues and some characteristics in terms of how do we generate traffic in this type of network, and as a consequence what we have to do to control it. And I will start with voice coding. It's not really important whether we start from voice, audio, or video. It doesn't make a big difference, so we will start with voice coding first. And the objective of this part is not to give you a detailed way about coding techniques. There are classes. If you are interested in this type of topic, you can go to those classes. You will get a lot of details, and there is a huge mathematical formulation behind this concept, etc., etc. We are not going to do that. We just want to understand which are the main coding techniques that can be adopted and the consequence that this coding technique can have on how we generate data or packets if we are using this type of application as users. Okay, so well, you know that the human voice is an analog signal, and so it means it's a continuous time signal, which is assuming an infinite set of possible values, of course within a bounded interval because we have bounds on the power that we can generate. And that's how the signal is generated in the acoustic domain. And this signal is typically translated in a signal that is more suited to be sent over cables or over any transmission medium, which is typically either electric, electronic, or magnetic, or something like that, but still analog. Now, what we want to do is to transform it in a digital signal, in something that we can easily represent using bits. Okay, and that's the typical process of analog to digital conversion that has been done in many domains, and that is typically done even in phone networks with the plain standard system, which is analog in the first segment from the user to the first node, and then becomes digital or numeric until the last node, and then it's become converted back to the analog domain, unless you are using ISDN phones, which instead are numeric starting from the user premises. So you directly convert the human voice, pressure voice, into a numerical signal at the user premises. The main process that we run to do this conversion are called sampling and quantization. We already have discussed that. The basic idea of sampling is to sample at different time of instant, which typically are regularly spaced, the signal that is generated by the user. This signal has a bandwidth which characterizes it. Okay, the larger the amplitude of this bandwidth, the larger the possible variations of this signal over time, and the larger the bit rate we need to represent it in a proper way. So there is a direct relationship. And in particular, we know that given this limited bandwidth in which we can represent this signal, we need to sample at the sampling frequency through the Shannon theorem, which is double the amplitude of this bandwidth which characterizes this signal. Okay. Typically, what you do is that you low pass through a filter these signals to make sure that it's really bandwidth limited. That typically introduces some distortion, limited distortion, and then you sample at a speed which is compatible with this rule. After that, you get a digital time signal, which may assume, however, at this point infinite possible values, right? Because you are simply taking this analog signal at different time instant. This is sometimes called as PAM, or pulse amplitude modulation signal. It's something like that here. So you have, I'm pretty sure that all of you know that this is the input signal. This is the pulse train that we use to sample the proper values of the original signal, and we get these PAM samples, which of course are similar to this shape, but they are discrete values. And at this point, we have actually an infinite set of possible values, as before. Of course, after this, you could actually go send these samples as they are, go through a low-pass filter to rebuild this output signal. This can be done. This is not particularly efficient, and this is not digital transmission, okay? Because we have, in any case, infinite possible values here, so we need infinite bit to represent them in a proper way. What we are typically do instead is that we quantize these values on the y-axis. So we select a given number of levels we want to adopt to represent our signal, and this level is selected a priori, and this gives you the well-known quantization error. Why is that? Because any level in the original signal which is within a given band of values is represented by a single value. So we are making an approximation error, okay? This approximation error depends on the amplitude of this interval, which is called delta, and this amplitude depends on the number of levels you want to use to represent your signal. The more levels you will have, the smaller will be the quantization error, the more bits you will need to represent this signal. If all the intervals have the same amplitude, this is called uniform quantization. And if you are operating over 2 to the n levels, you need n bits to represent each level uniquely. This is the quantization error. And the beauty of this quantization error, this is an error that we pay a priori, so we know that we are distorting the signal by this amount, okay? So the received signal, even if you properly receive any bit, will be affected by this error that we select a priori as acceptable, okay? But at the same time, if you never made mistake in the bit sequence recognition, that's the only error you will introduce on your received signal. So there will be no contribution due to the noise introduced by the channel or by their intermediate devices. That's the example of quantization error. Okay, you see that here in this example we have 3 bits. 3 bits correspond to 8 levels, so it's a very coarse quantization, okay? And the idea is that you sample at given time and you represent the value with, for example, this number which represents the value, average value within this interval. So this will be a quantization error because we'll actually, instead of using this signal, we will reproduce at the receiver using this sample here, and the same here and the same here. Okay? I think this is well known to everybody, fairly known. That's the so-called PCM. This is a pulse code modulation, which, as we know, applied to a voice signal gives this speed of 64 kilobits per second, which is derived from a 4 kilohertz bandwidth amplitude, which makes 8,000 samples per second, and with the choice of using 8 bits to represent the amplitude of our signal, which means 2 to the 8 different levels. Okay. This is called PCM in general. You can apply this technique to any signal. This is just a technique which can be applied for any bandwidth limited signal. Now, bandwidth limited signals are typically bandwidth limited by themselves, or by the fact that we want to limit them by a filter, but at the end we have a bandwidth limited signal. And for any bandwidth limited signal, regardless of the proper characteristic of this signal, we can adopt this technique. For example, for an audio signal, we can do that. With CD quality, you will get out with this 700 kilobits per second, roughly speaking, of bit needed to send a CD. with an audio signal with CD quality. That's the idea. So you have an analog to digital conversion, you send the bits, and you reproduce at the receiving end. That's a more precise representation of the human voice power. That's, of course, average among many, many speakers. So it's an average representation. And you see that at 4 kilohertz, this is the 4 kilohertz, you see that we are not starting from 0. We are starting, however, from fairly low frequency, okay, around 50, up to, roughly speaking, 400. Actually, it's a little bit more than that, okay, but at 4 kilohertz, we have a ratio between the maximum power and the power that we have at 4 kilohertz, which is about 60 dB. So it means that even if we are actually able to emit potentially a different set of frequency, at the end is not so significant in terms of what you perceive. Okay. How do we measure the coding quality? That's an example of coding. We will see many of them. Well, there is no direct way or engineering-based way of measuring the quality of a coding scheme. You can, of course, measure the bit error rate. You can measure many, many things, but at the end, none of them is a good representation of what we as humans perceive as a good or bad quality. Okay, there is of course a correlation, but it's not direct. So it would be very difficult to measure the quality of a coding scheme by any measuring technique that we typically use to measure something else. Okay, so what has been established in the domain of voice coding is that the way of measuring the quality of a voice signal, remember that here the goal is not to have the best possible quality, but to have a quality that allows us to clearly understand the speaker and possibly recognizing. Okay, we know that the coding, even the PCM with 8 bits, is not perfect. Okay, and indeed, if you speak at the phone, your voice, you will perceive that is a little bit distorted, right? But this is considered to be acceptable. And in order to measure the metrics of different coding schemes, what you do is that you have a set of standardized procedures. You have hearers, people that hear standardized sentences that have been chosen according to their typical and important statistical properties, and you keep repeating these sentences, and you do that for many, many different types of speakers, and you code that with the different coding schemes, and you ask the people that hear this signal to score them from 0 to 5. And that's called mean opinion score, and that's how we really measure the quality of a given. So it's a quality measure which depends on how do we perceive this signal. It's not absolute quality. It's how humans perceive this signal in a good, bad, or so-and-so, or very good or very bad. It's from 1 to 5. 1, it means basically not acceptable. 5 would mean perfect. This is a summary of what's happening in the so-called PCM. With 12 bits, you will get 96 kilobits per second. This has been standardized, but this has also been considered to be too high quality. And the point is, from now on, in this type of coding, is not to improve the quality of the speech. We can do that. The goal here is to reduce the bitrate while maintaining a good perceived quality. That's the goal of any voice coding scheme that have been studied in the last 30 years or something like that. Okay, so the goal is to reduce the bitrate needed to represent the original voice signal, minimizing the distortion perceived by a human hearer. Okay. So the first idea is, and all of them basically are trying to exploit some information related to how the human voice is really produced. So which are the peculiar characteristics of human voice? Up to now, the coding scheme is just give me the frequency band over which you produce this signal, and then I will code it. Okay, but you may have very, very, very different type of signals. Even if you limit them from 0 to 4 kilohertz, okay, you can generate very different type of signal information. Can we somehow exploit this type of information to obtain some benefits? The answer is yes. the first idea, which is really giving the so-called logarithmic PCM, which is the one I was mentioning when I was saying that we have 8,000 samples per second with 8 bits to represent, is actually a PCM scheme, not uniform. It's logarithmic PCM scheme. And why this is more efficient? So you see that we can basically reduce the number of bits with respect to the previous case. We had 12 bits in the previous coding. Now we can get out with 8 with very similar quality, perceived quality. Why is that? Because indeed the human voice is more often, more frequently concentrated in an area in terms of amplitude which is not reaching the maximum possible amplitude that we can have. So within this set of minimum maximum values, the values here are much more frequent with respect to the values that you may have in this area here. So by exploiting a non-uniform quantization, we will basically better represent, with a smaller quantization error, the more used signals, the more popular signals. Whereas we increase the quantization error and maybe by a significant amount. You see that if you compare this uniform quantization with this step, you see that here the quantization error is huge. Okay, but who cares? We are very rarely going to use it. Signals in that area are very, very rare, and so at the end we get a better quality with a smaller number of bits. That's called also compending. Okay, that's the most popular PCM scheme. Another idea comes from the fact that, given again the nature of the human voice, adjacent samples are similar. There is a huge temporal correlation among consecutive samples. Why? Because we typically speak in a smooth way. We are not exploiting the full bandwidth to continuously change the power level that we use when we speak. Okay? So if you statistically analyze human voice, you will easily detect that there is a lot of temporal correlation. Temporal correlation. There is a correlation between different times at which you sample the human voice. So the idea is to say, okay, why don't we exploit this information when we code our samples? Up to now, we code each sample in a completely independent fashion. So you take the value, you select the proper interval, and you code it. You take the next value, you select the interval, you properly code it, and so on and so forth. So you don't exploit at all adjacent information. Now, since we know that indeed, statistically speaking always, adjacent samples are similar, we can exploit this information and do what is called a differential coding, in which we are not coding each sample in isolation, but as a difference with respect to the previous sample. Is it clear? So the idea is to code again a given sample not alone in isolation, but with respect to the value assumed by the previous sample. Is it clear, the idea? That's called differential coding. We are seeing it here. We will see that in video. We will see the compression techniques are very similar. Of course, they are exploiting the different characteristics of the signals, but the basic idea are very similar. So that's the idea of differential coding. I'm taking the value, and instead of coding it in isolation, I'm representing it as a difference with respect to the previous sample. Okay? The intuitive idea, then you can much better formalize, we don't have the time and the interest to do that. The intuitive idea is that since there is a lot of correlation, the value of the difference between two samples, let's go back to this, where is it? Here. Consider, for example, these two samples here. This is a very ideal case. Basically, sorry, these two samples, the real one. What? Oh no, not the real one. Sorry, the represented one here. Okay. Now these two have, in this case, specific case, exactly the same value. Okay. In this case, they have different value, but you see that the value of the difference signal, which is this minus this, the distance between the two, the value of the difference signal between two adjacent samples is much smaller than these dynamics. in general. Okay? The value, the difference between these two signals as a dynamic, the dynamic is the maximum possible value that you typically take, which is much smaller than the possible total dynamic of your signal. Okay, is it clear? So as a consequence, you can either reduce the number of bits to represent the difference with the same quality, or you keep the number of bits, but you increase the quality. You can play both games. Okay, that's the idea of differential coding. So that's the idea. You take a sample and then you compare it with the previous estimate, and then you code the difference between the two. Of course, you can extend this concept by using not only the previous sample, but a set of previous samples. Okay, so you can extend the same concept through what is called a weighted difference, in which you typically take a set of n, capital N, previous samples with different weights. What does it mean? The closer one are more important, are more correlated, the older one are less correlated. So instead of having a window of 1 in which you take only the previous sample, you take a set of previous samples. So it's the same line of thought with slight variation of that. Okay? And you can optimize this coefficient here, statistically speaking. You can analyze many human voice signals. You can analyze them offline. You can come out with the optimal set of alpha, which is allowing you to reduce the number of bits without touching the perceived quality. Okay, so this optimization can be done offline. The same holds for how much you weight the current samples with respect to the previous sample. Alpha can be 1, but you can demonstrate that the optimal solution gives an alpha which is all equal something around 0.9. Okay, optimal means that allows you to optimize, reduce the number of bits by keeping the same quality. Okay, of course, many of those techniques have been tried, have been made score, and some of them have been even standardized. Okay, so they are available. The last step in the same line of thought is to exploit another characteristic of the human voice, which is that it's not really a stationary signal. What does it mean? Well, you know the formal definition, at least most of you. Intuitively speaking, it means that if you analyze a human voice speech at different instants of time, they are not always the same, physically speaking. So the spectral characteristics are similar, but are not identical. Okay? So if you really want to optimize things, you can optimize the quantizer and the coefficients and all of these kind of things in an adaptive way. So you need to analyze your signal for a longer period of time, of course, not only sample by sample. You have to define dynamically which is the optimal set of alpha for that period of time. You need to declare this set of alpha to the receiver, because the receiver should also be adaptive. Okay, so you see that the system is becoming significantly more complex. Okay, in the previous case, I just have an offline computation. I have my alpha, I'm using them at the transmitter, I know the alpha at the receiver, and that's it. Nothing else to do. Here, the system is much more complex. I have to estimate them, to compute, to communicate the estimation to the receiver, and so on and so forth. Again, also with this adaptive PCM, this is the adaptive PCM, and then you can adapt the same idea of adaptive coding to the ADPCM, adaptive differential PCM. So you have PCM, differential PCM, adaptive PCM, in which you change the level of quantization according to the stationary behavior of your signal for a given time frame, or adaptive DPCM, okay, which combines the differential idea with the adaptation of the coefficient. This has been standardized. This is a fairly popular standard. That's what I'm mentioning, which is called ITU G726, which has a rate of 32 kilobits per second. So it's half of the logarithmic PCM, which is the standard one, thanks to the fact that you can manage a good quality with 4 bits per sample only. Okay? You have some more details here on how you can implement the adaptive. There are two slightly different ways of doing that, but it's not so important. I mean, as I said, we are not really interested in going deep in the coding techniques. So that's the first family of algorithms. So you have the basic idea. You have a PCM, you know the bandwidth of your signal, you know that you have to sample at a given speed, and try to exploit some statistical information to evolve over this basic idea through, for example, the differential idea or the adaptation or the PCM or of the differential scheme. Okay? So that's the framework. Basically, the best we can do while keeping a reasonably good quality is this standard here. So we reduce by half, 32 kilobits per second. The mean opinion score of this coding is a little bit lower than the mean opinion score of the coding we are normally using in phone networks. Okay? So the quality is not exactly the same. That's the first type of approaches. There is another type of approaches, which is generally speaking called vocoder, which is based on a completely different principle. The idea is to further reduce the bit rate. Just to give you an idea, on our cell phone, we send a much lower bit rate than those. Okay? The GSM coding, for example, is using this type of idea. And the idea is to develop, as written here, a production and perception model of the human voice signal. So humans generate the voice, which is a pressure wave, according to a given process, right? Now, the idea is to emulate this process and synthetically generate a human voice speech, okay, according to some set of characteristics that we can extract from the original signal. But the signal is really locally built at the receiver according to a synthetic model. Okay? That's the main idea of any of those schemes. We will see two main schemes of this type. So at the source, you analyze your voice. You send some parameters that describe your voice signal that the receiver is able to use to set up its local generating machine, which is generating human voice. So any of those smartphones has a local process which is able to generate something which seems, according to our perception, human voice. Okay, that's the idea. So in order to do that, we need to know a little bit about the process of building or generating a voice signal. Everything is started from our lungs. We generate an unstructured signal. It's a pressure signal which is very, very similar to white noise. So it does not have any spectral characterization, what is coming out from the lung. Okay? And of course, depending on the power that we use to emit our voice, we have a different gain, but that's fairly easy to be estimated. Okay? So the first thing that we need to estimate at the source is the so-called gain, which is related to the emission power of our signal. And then this unstructured in frequency, in the frequency domain signal, goes to the vocal chords, which are here, which are going to break in this moment, you see, you hear. And the vocal chord, very roughly speaking, as a first approximation, they can be in two different states, closed or open. And depending on whether they are closed or open, the signal that is reaching our vocal tract can still be an unstructured signal like the one generated by our lungs. And that generates the so-called unvoiced signal. Okay? For example, while you are whispering, you are talking in this way. All of the signals are unvoiced. All of those signals are unvoiced. Voice signal you recognized because they have what is called a pitch, a fundamental frequency, which is what characterizes our speech. Okay? Every speaker has a different pitch. Okay? And the pitch is exactly that type of frequency information we can extract from voiced signal. Voice signal, for example, are vowels. A, E, O. You see that there is a kind of, not music, but a regular sound behind it. Okay? So that's the basic idea. How do we build? And so we can exploit this to reproduce at the receiver. As long as we are able to understand whether we are using a white noise or this periodic oscillation signal characterized by the pitch. Whether we know the gain and the pitch, we can rebuild synthetically this signal. Okay. Now, in all of these pictures, there is one piece missing still, which is, of course, how do we distinguish, how we emit the different, they are named phonemas. Okay, and that's due to the vocal tract. It's a cavity. Basically it's the filter in which we can modulate and change the pressure wave that we generate by using the tongue, by using the mouth, many things. But at the end, this translates in a given frequency filter. So at the end, what we call phonemas, which are not the single letters, is something a little bit more elaborated. Okay, they are called phonemas. These phonemas are typically characterized in frequency, and in particular they are characterized by a very limited set of frequencies which are called phonemas. There is one principal frequency and then some other one. Okay, now the idea here is to identify which is the phonema used by the user, and then use this phonema at the receiving end to reproduce what the user has generated at the source. That's the basic idea. Is it clear, the idea? So what's going to happen is that I take the human voice, I have to analyze it. There is no concept of sampling anymore. You analyze the human voice in blocks. This block size is typically 20 milliseconds. Why 20? Because studies have demonstrated that that's a good balance, and that's fairly related to how long a phonema really lasts. So you take 20 milliseconds. In this 20 milliseconds, you extract the gain, the pitch, which is the fundamental frequency. You need to understand whether this phonema is voiced or unvoiced, so whether you have generated with the vocal chord in different voice, that's a binary information. Then you have a given set of coefficients which represent this frequency characterization of the phonema, and that makes a total of 52 bits, depending on the number of bits that the standard tells you to use for each of those values. What does the receiver do? The receiver rebuilds the filter through the coefficients. It sends to the filter, which is a passive device, an excitation signal which is either white noise or a train of pulses at the pitch frequency with the proper gain. And that's it. The resulting rate of this vocoder, which is called LPC, linear prediction code, I will tell you in a moment why it's called LPC, is very little, it's very low, it's 2.6 kilobit per second. Now this has a very limited quality. This can be used for applications in which the only thing that you really need to understand is what the speaker has said, full stop. You just are only able to understand the speech, no ability to recognize the speech or nothing like that. It's a very, very basic scheme, and it has been implemented in user in some military communication systems. Okay, it cannot be used as it is for commercial applications, but that's the idea. In practice, this is what you have at the receiving end. You have either the pitch period or the noise generator. You have the selection of one of the two. You have the gain. The voiced signal is set up with the pitch value that you receive, which is this typical frequency of characteristic. And then you go through this filter, which basically represent the vocal tract, which represent the phonema. Okay, that's the idea. That's how you generate, according to this scheme, at the receiving end, in a fully synthetic way, the signal. So you are only sending the bits which represent the information you need to set up this circuit, this generation circuit. You need the gain, you need the pitch, you need the flag to understand whether you have to use either a voiced or an unvoiced signal, and you need the gain, and that's it. Okay? Now, it can be demonstrated that this technique is actually equivalent to a, it's written somewhere here. Where is it? Here. Turn out that this is very similar to what you obtain in a DPCM scheme. Okay, so this is not easy to understand in an intuitive way, but this is actually what's happening. Okay. Now, can we still use the same basic idea of synthetic generation, but with improved quality? The answer is yes. This has been known for years that this was possible, but it requires a huge power computation that until a given year in the 90s was not practically available. So when we could exploit a significant computational complexity at the transmitter and at the receiver, so we need to have sophisticated devices, at that point this type of approach can be used to improve the quality and to get something which is commercially usable. And the idea is the so-called CELP, or code excited LP scheme. Now, very simply, the most critical part in the scheme that we have named LPC, the one that we have seen up to now, is in the limited use of only 2 excitation signals, because the remaining part is fairly good. The phonemas can be easily extracted, and they represent very well what you want to say. The gain is easy, the pitch is fine. The very limitation is in the fact that when you analyze 20 milliseconds of speech, very rarely it's fully voiced or fully unvoiced. And instead, at the receiver, you have to make a choice. And so that creates the most perceivable distortion at the user. So the idea is to say, well, why don't we improve the set of excitation signal? Why we don't extend it? And that's exactly what we do here. We assume that there is a fixed number of excitation signals, which is typically 1024, okay, which do not represent words, letters, phonemas, nothing like that. Okay, don't make this confusion. Otherwise, it will not be possible with 1024 signals to represent any possible speech in the world in any language, as you can imagine. Okay, it's not that. Is the set of signals we can use to, at the receiver, excitate the filter, which is still extracting the phonema, etc., etc. So everything is the same. We are only changing the type of signal we can use to excitate the reception filter. And clearly, instead of having only 2, we can have up to 1024. We will choose these 1024 according to some statistical criteria that can be analyzed offline, and that improves very much the quality of the speech, up to the point that we are using this type of technique in commercial devices like the smartphone we are really using. Still, the quality, as you know, being a user of both the fixed and this type of phones, is not exactly the same. Okay, the human voice through the smartphone, the cellular phone, is more distorted, is less recognizable than the human voice that you can get for sure in person, but also over a plain phone in the plain phone system. So what does the source do? You extract all of the parameters as before, the gain, the filter, etc. And then you compare the sample signal that you have here. This is the sample signal, which is not a sample, is actually 20 milliseconds sample, okay, with what you would obtain by using signal 0, signal 1, signal 2, signal 3, up to signal 2 to the n-1, the full code book. So you try brute force approach, all of them, you get the one which gives you the minimum error with respect to the real signal. So that's the real signal, that's the synthetic signal that the receiver would create by using one of those elements. You take among all of the signal that the receiver can reproduce at the source the best that match the current signal, the one which minimizes the error with respect to the current signal. Is it clear? Once you have selected, what you will send is user instead of the flag, which was binary. We need to have a number of bits which are able to tell us use this signal here as a receiver, signal 22. So we slightly increase the bit rate because we need more than 1 bit to do that, okay, log 2 of 1024, but that's the basic idea. And this is a picture of the coding quality of the different. So this is the vocoder, this is the MOS. How do you grade the different scheme? Okay, this is the vocoder, and these are other type of coders. This is the PCM, okay, with 64 bits. This is the logarithmic PCM. You see that the MOS of this one is almost as good as the one of the PCM with 64 kilobits per second, and you see that the MOS of this coding, okay, is with a reduced bitrate as good, almost as good as the other one. Okay, so in this area here we have 3 good coders which you can use for commercial purposes with their respective bitrate. Here we have a bad one. Here the same type of coder, if you reduce the bitrate, which is of course possible, of course you reduce by a significant amount the quality that you perceive. So you can play 2 games. Given a coder, try to optimize the performance, and once you are above 4 you are satisfied and you stop here. Or if you want to really reduce, you know that you can reduce the quality, but the price you pay is here. The MOS of each coder is becoming worse and worse. Okay? Now, in terms of what is important for us, besides having some idea about the coding technique that we use, basic concept here is that if you look at the original PCM scheme, which is coding this, where is it? Here it is. Okay, in this case, if you made a mistake in detecting at the receiver this level, okay, this is actually tolerable from the perspective of the user, the human user. Why? Because basically what we do at the receiver is a kind of a process in which we smooth out this signal, we filter it out, okay, and this filtering operation would of course compensate this error on a given sample. So single error or few errors are fairly tolerable in this type of application. Of course, when you start compressing differential coding, etc., any error becomes immediately more important. The same holds for GSM. Okay, the same holds for GSM, which is the CELP coding, in which if you start losing something, since every information is really needed to rebuild in a proper way the original signal, you start having a lot of problems in understanding. Okay, so that's the first thing. First observation, the bit rate required by the application is variable depending on the coding scheme that you use. But the more you compress, the more you reduce the bit rate, the more you are sensitive to the errors. These are the most important messages from our perspective that we can extract up to now. Any question about that? Okay. Now, very quickly, some hints about audio techniques, which I don't want to go into too many details. Some of the information that we have here have some importance also for the voice coding, because audio coding techniques have again the same idea. Try to match the quality of what we transmit and receive to which are the user needs in terms of human ability of hearing things. So we are going to exploit, to reduce the bit rate, the perceptual system of the hearing system of humans. By the way, I forgot to say something about the voice. There is another difference between the first family of coder and the second one. The first family of coder is able to reproduce any signal that you send over the phone, any signal, with the only limitation that is cut to 4 kHz. So you have a limited bandwidth, and that of course can distort if you're trying to use it to send, for example, music. The music is horrendously distorted, but anything that you generate with that bound of 4 kHz, you can send and you will receive with the same quality. The second type is instead very much oriented to human voice generation process. You try to extract a phonema. As a consequence, if you load the system with something which is unrelated with human voice, the coding that you get is much worse in terms of quality with respect to the coding that you can get. In other words, the coding scheme that you are using in smartphones or in any system that want to reduce the bit rate can be used for human voice basically only. Any other type of signal that you can send over that is much more distorted with respect, for example, to the plain PCM or anything else. Okay, that should be taken into account as well. So, for example, the background noise that you typically, even if you don't know, that you typically send over the phone is much more better represented on fixed phone lines with respect to the GSM schemes. Yes. No. What we are talking here is about how do we represent the human voice. Human voice starts when the connection is on and the circuit is available. Everything else is in the numerical digital domain. It is just based on sending bits. So you represent those digits with bits and you send it. This has nothing to do with that. We are only talking about voice coding here. Okay, so you mean during not during the opening phase. No, in that case, if you have, and indeed we have a pulse generation system, okay, the modern system of pulse generation, in that case you code it normally, as according to this, but at the receiver, that phase is fairly easy because you have to detect 1 among 10 pulses. So making mistakes on that is very difficult. So it's not a complex coding scheme. Okay. Anything else? Okay. So about audio. Now, audio, well, first thing, it requires more bandwidth. Why? Because with audio, we have a much larger bandwidth. Now, is it true that we are still hearing with our hearing system, which is the same as before? But our hearing system is much better in terms of frequency that we can hear with respect to the set of frequency that instead we are able to generate. So the spectrum of what we can hear is much larger than the spectrum of what we can generate. So we want to be able to hear very different type of sounds generated by very different type of devices. And typically, we assume that the audio bandwidth is ranging between 20 Hz up to 20 kHz, so 5 times larger than the human voice bandwidth, okay? With a dynamic about 96 dB. Okay, there are some characteristics that we can exploit to do the coding. The first things that you have to know is that we may generate sounds at very different frequencies, okay? Now, suppose that you have a synthetic generator that is generating exactly one frequency, something which is, of course, not realistic. Our ability to distinguish among sounds which are at a given distance in the frequency domain decreases as the frequency increases. So our resolution capability in the frequency domain is higher at lower frequency. It becomes worse as you move to higher frequencies. Okay, first observation. The same observation holds for the amplitude. We don't have the same ability, the same capability in distinguishing a close signal with a different level of absolute amplitude of the signals you are considering. So with the same distance, it's easier to distinguish them if the power level is smaller. It's more difficult to distinguish them if the power level is larger for the same absolute distance among samples. Okay, these are characteristics. So our ability to distinguish becomes worse. We can exploit this to somehow do that. Furthermore, the perceived amplitude of a signal depends also on the frequency. So if you inject the same power at different frequency, we will perceive them with a different power level. Okay. What we typically do when we analyze, not only for coding purposes, the audio signal is that we identify the so-called critical bands, which are sequence set of adjacent frequencies over which the perceived amplitude is more or less similar. So within that range, we perceive the frequencies in the same way. What does it mean? If you generate exactly the same power level, we will perceive it in the same way. If you change frequency band, this is not true anymore. Critical band is not true anymore. The size of these critical bands also varies at different frequencies. They are not constant over the frequency domain. Okay. After many analyses, as a first approximation, we typically subdivide the audible spectrum in 26 critical bands. These are 26 set of adjacent frequency. Within each band, our ability to detect the amplitude of the signal is more or less constant. And this is a sound perception graph, so that's the sound pressure level as a function of the frequency. Okay, you see the speech is about here. This is a logarithmic scale. Okay, so the frequency band by speech ranges from here up to here, which is a little bit more than 4, you see, whereas what we can use. And then we have also sensitivity in terms of ability to receive a given power level. One of the main effects that we use in audio coding to reduce the amount of bits we need to represent the signal without changing the perceived quality is the so-called masking phenomena. The masking phenomena means that there are signals which are not audible, of course, which have a smaller power, if they are close to other signal with other larger power, either in time or in frequency. So there is a threshold below which we are not able to perceive any generated signal if the signal that we perceive, the amplitude of the signal that we perceive, is too close with respect to the considered signal, either in time or in frequency. Of course, this masking effect is non-linear, is non-uniform, is non-constant. It depends on the time, on the frequency we are considering. And there are some other dependencies from the amplitude, for the frequency, in some cases from the type of masking signal, because it can be noise or it can be a tone, which is a pure frequency generation. So it's very complex. It's very, very complex. That's an example of frequency masking, which states that if you generate this tone here, okay, this is the mask, which means that we are not able to perceive, sorry, this white part here, we are not able to perceive any signal generated in this frequency domain if the power level is below, in this white area, below that threshold value. Okay, that means there is no point in encoding it. We don't need to code it because we are not able to perceive. Now, of course, this is statistical. We can do that on a statistical basis. So we will analyze and we will generate a model of average perception system, and we will tune our coding scheme in order to be optimal, whatever optimal means, with respect to this average behavior. It means that any of us, which is not exactly average, may hear or may perceive a larger or a smaller degree of perception error depending on how far is our perception system with respect to the average one. Okay? So let's come to some coding rates. If you take a CD quality and you don't compress it at all, you consider 2 channels, it's a rate of about 1.4, 1.5 megabit per second. Okay. You can use also in this case AD-PCM coding techniques, adaptive and differential, because similar concepts apply also for this type of signals. Of course, some signals are more correlated in time, which means that by using a differential you will gain a lot. Some other signals may be, remember that here we don't know what we are going to code exactly. Whereas in the previous case we know exactly the type of source is generating the signal. Here it depends. It can be music, but it can be also something different. It's anything we can perceive. So it's a little bit more complex, the scenario. And at the same time, adaptation is typically useful, but again, you gain a lot if this signal is changing significantly over time. You gain very little if instead this signal is more or less stationary for the whole time, because at that point, this need of defining and computing this adaptation information and sending it does not pay off. Okay? Clearly, the approach of source modeling, the one used in LPC on CELP for voice, cannot be used because the original source is too various. We have too many sources. Okay. Now, if you limit, in principle, if you say, no, I'm limiting my audio coding, for example, to signal generated by a rock band. Well, the rock band is typically using a guitar, etc., etc., etc. You could, in principle, think about doing something similar to that, okay? But in general, it's very, very unpractical. So typically, what we do is to use the so-called psychoacoustic coders that exploit the characteristics of our hearing system in a perceptual way according to the phenomena that I described previously. So the masking one, we are exploiting the masking one, we are exploiting, etc., etc. MPEG, which is a coding group, standard, international standard coding group, which has defined also the video coding techniques that we will discuss a little bit later in a moment, has also defined standard for audio signals. We specify many, many things. We specify which coding algorithm you have to use, which creates a given stream of bit, and then it specifies many, many other things. Okay, for example, the bit stream format. How do you organize this bit? Which type of additional information you send? For example, in the adaptive scheme, you have to define when you are going to send the new parameters that you have to use at the receiver, because they change over time. The alpha coefficient change over time. So you have to envision that periodically or in some way you should have in your bit stream the ability of sending these coefficient values, and so on and so forth. And also the so-called conformity tests, which are used to guarantee that your coder that you are selling is conformant to the standard. That's another important issue, right? There are tests that are used to check and make sure that when you build a coder is really operating as it should according to what is written in the standard. We will come back to the aspect of the standard later when we will discuss about QoS efforts in the standardization process. The standardization process is absolutely needed and fundamental, and should be defined in such a way that it does not prevent, of course, the possibility of having different providers which provide this solution with different algorithms, with different technique, and you can compare them and select the one that you prefer. So the standard should avoid, should be written in such a way to avoid, to make it impossible to have this competition among different products. Okay, the standard is there only to guarantee interoperability. Regardless of the fact that I'm using coding developed for Android or coding developed for the iPhone, we should be able to speak in any case, and that's what the standard really fixes. We are typically talking here about lossy compression. There are other types of compressions. We will see them in the case of video, which are lossless. In general, lossless compression is possible, but is less efficient. We gain less, basically. Lossy compression is more efficient. Of course, we reduce the quality of the produced signal, but the game is that, again, if we create something that from a perceptual point of view has the same quality of the original signal, we have reached our goal. Now, there are some expert listeners or self-labeled expert listeners that claim that they are really able to feel a difference between the coding A, B, and C, and D, or even the big difference with the best coding we have, the digital coding. We can feel the difference with respect to the original analog signal. I don't know whether to trust them or not, but at the end here we are talking about statistics. So also in this case, you create the coding, you have a set of standardized signals that you make them hearing, you make them having the score, etc., etc. And at the end, if you are using the most powerful coding scheme, so the one that have been standardized, most of the people are not able to distinguish this type of coded signal with respect to the original one. Okay, and you can obtain compression ratio which are very high, up to a factor of 5 or 6. And the basic idea is PCM. So you take the input signal as PCM sample, you make a transformation in the frequency domain, okay? Then you divide the spectrum in the 32 subband of same amplitude, and exploiting the psychoacoustic model, what you are doing basically is to assign a number of bits to each subband, which is good enough due to the fact that we are hearing in this way in this subband and in another way in the other subband. That's the basic idea. And of course, you are also exploiting the masking phenomena. So if the amplitude of the signal in the subband is below the masking, you are not going to code it at all. Otherwise, the number of bits is enough to ensure that you control the quantization node below the masking threshold. Okay. There are some details here. This is just a graph that tells you as a block how the process of creating the signal here on the top part from left to right goes. So you decompose in subband, you compute the mask, you allocate the bit to each sub, and then you send the bit stream. This is not formatting, but it's formatting. And at the receiving end, you do exactly the other process in the reverse order. This can be skipped. Some numbers here. MPEG-1 is coming with 3 sampling frequencies, so of course with different quality and different bitrate as well. And the bitrate is constant, and it depends on which type of subset of parameters you select. So if you have a coding scheme of this one, you can set up parameters. And so this can be done offline, or can be done online through a negotiation process with the receiver, for example. That's another issue. You may have a transmitter which is able to select among several types of coding scheme, the receiver is maybe only able to receive according to a subset of them. Of course, you have to select at the transmitter some set of parameters that will make able the receiver to reproduce this signal. Okay, this typically depends on the bit rate and on the speed of the receiver. So the standards tell you that you can have a full set of features of coding scheme at different speed, but all of those schemes are fixed bit rate. So once you have selected one coding scheme, you will transmit at that constant bit rate. Okay, and you see that the bit rate is fairly limited. There is also the option of supporting variable bit rate through, of course, a negotiation process, etc., etc., but typically is not used with this type of coding. Yes, I forgot that. Okay. Another information that is maybe of interest is the following one. What are layers? Okay. Layers are a way of coding your information that may be useful in under some particular and peculiar circumstances. Let me give you an example about that. No, it's not this. Okay. Okay, when you send a voice signal, you only have the problem of making sure that the transmitter and the receiver agree on a given coding scheme. Okay. More often, and especially when you have not a point-to-point communication, but when you have a point-to-multipoint communication, so a multicast group of speakers, you may typically have the problem of selecting a proper coding scheme. Now let's simplify. Suppose that this is the transmitter. You want to send this signal from here to a given subset of users. So you have a given set of users here that are interested in receiving this information. However, they have different capabilities. So suppose you have an audio conference, but some of the receiver can exploit a PC through maybe a local area network access. Some other of these receivers have only a smartphone and they can access only through the wireless phone system. Now, even only in terms of bitrate capability, in terms of medium, there is a big difference, right? Then you may have the problem of ability of processing speed to decode the signal. But let's forget about that. Let's suppose that the receiver is able to process any coding scheme, but you may have a bottleneck in terms of bitrate you can able to receive for different reasons, right? So suppose that you have three types of receivers: the red one, the blue one, and the green one. And red can receive at speed which is 10 whatever, okay. The blue can receive at a speed which is instead only 5, and the green one can receive at the speed which is 3. Okay, and for simplicity, suppose that this bit rate or whatever are fixed. Okay, now you have several possibilities as a source. First possibility, you send only the green signal. That's possible, right? You send the green signal, what's going to happen? The green users, suppose that the green user is this guy here, we get it properly. Then we have one red and two blue. And what's going to happen? It's going to happen that the blue and the red receiver will be able to get, because the coding scheme is the same. You just select a given set of parameters that any of these receiver is able to understand. They will receive with a quality which is reduced with respect to the maximum possible quality at which they could receive. So in other words, if you are using a PC with Skype and you are using a smartphone, everybody is getting the same quality as if it was using a smartphone. Okay, that's one possibility. So you go to the minimum. That's the first choice. So you go with the green only. That's choice 1. Choice 2, you generate the 3 signals. That's the second possibility, right? At that point, every receiver is receiving with the best possible quality according to its local problem, its local capability. Everybody is satisfied. The problem is at the transmitter. Now, the number of coding type is not huge. It's not scaling with the number of users, which would not be possible, of course. Okay, that would look similar to saying, okay, I'm treating a multicast with n unicast, independent n unicast. It's not like that, because here we are talking about coding possibilities, which is not scaling linearly with the number of users. Okay, so in any case, the number of flows that you have to generate is fairly limited here, even if the number of users can be fairly large. Still, you have an increasing complexity at the transmitter because you have to generate in parallel different coding schemes. Okay, is it clear? The third possibility is to generate a so-called layered signal. Now, this layered signal is neither red, green, or blue. It's very similar to the red one because it contains the full capability in terms of quality, but is composed, organized in such a way that if you want to extract the red or the blue or the green signal by extracting a subset of bits or packets or whatever, depends on how you organize the stream, that will be possible. So natively, you start generating in such a way that at the end you can receive with the red quality, if you wish, by getting everything, but it's not like the red signal, which is only for people are able to get the red, but it's composed in such a way that you have the green signal plus an additional layer which allows you to move to the blue signal, plus an additional layer that allows you to move to the red signal, in which you have more information and more information. Is it clear? So it's a different way of composing at the source the signal. That's called layering or layered approach. That is a layer. In the layer you have the green plus something that will make the blue. So these two things together will make the blue, and the blue plus something together, they will create the red. Okay? That's the idea. Of course, the bitrate of this layered signal is going to be slightly larger than the bitrate of the red signal, because you need some additional overhead to organize your bits and to be able to understand how to extract the different paths. So it's comparable with the red in terms of coding rate, bit rate, but slightly larger because you have a little bit more of overhead. Okay? So these are what the layers are about. And in MPEG-1, 3 layers are envisioned. One, which is called base layer, which is the one which is guaranteeing the minimum information, the smallest quality, and then layer 2 and layer 3, which enhance system performance by adding something more. Okay? The MP3 format is actually MPEG-1 layer 3 standard. We can skip the technique in which we obtain the layers here, it's not so important. And finally, some numbers for MPEG-2. This is much more sophisticated because it can have up to 5 hi-fi channel plus a low frequency one. You can have up to 7 audio channels in several languages on the same bit stream. Okay, you can have 3 sampling frequencies plus the frequency we had in MPEG-1, and it's partly compatible with MPEG-1. Okay, in the sense that if you have an MPEG-2 decoder and you have an MPEG-1 coder, you are able to detect it. Of course, not vice versa. Okay. What you can do is that you can encode and use MPEG-2 stream, formatting them in such a way that MPEG-1 decoder can extract a subset of this signal from MPEG-2 encoder. Okay, so there is a compatibility issue. You see that these standards are fairly old. Okay, we are talking about 20 years ago or more. That's basically it, unless you have questions. Yes. I put it in a very simplified way, but yeah, that's the basic idea. Now, of course, this is not going to work if the limitation of the receiver is due to the bandwidth access. Because if you have a limitation in the bit rate, you are getting the yellow bit rate, which is the largest possible, and you will not be able to receive it here. So if the limitation is on the receiver, it's fine. If the limitation is on the access link or in a given portion, you need to have cooperation with the network, and you need to have a device in that node which is able to extract the, for example, the green signal from the yellow one and forward on that link only that part. So in other words, if you have a node here, let's make a new picture here. Suppose that you have a network in between, okay? You have your nodes here, and then you have your receivers. And you generate the yellow signal which goes through. Now, suppose that here, okay, you arrive here, and this one is able to get the yellow, whereas the other one is only able to get the green. Now, you need to have here, in this node, which is the last one before the link that has this bottleneck capability, able to extract from the yellow stream the green one, in order to be able to send only the green flow to this decoder. Okay? Otherwise, it's not going to help if the problem is the network. So the decoder were not designed having in mind the network. They have been designed having in mind the point-to-point communication, okay, between a transmitter and the receiver. In that case, having a layered one could be useful. If you have a network in this scenario, and the bottleneck is not here, but is on the link bandwidth, you need to reduce this due to link bandwidth. You need to change your coding within your network. That's the only way. Otherwise, it's not going to work. Because on this link, you will send the yellow. The yellow is too large in terms of bitrate. You will have drops, and you will not be able to extract in a proper way the green signal of the receiver. I don't remember who was asking this question. It was you. Is it clear? So, of course, it's not the network which is doing that, but it's some device that is hosted close to the last network node in which you do that. Normally, this problem you have only in the access link. You are sure that within your network, if it's quality-based network, you ask for the yellow capability, and either you get it so that you will start the communication. If you don't get it, you will not. Okay? So that's what's normally happening. Whereas in the last link from the node network to the user, in which you may not have this tight control, you may have this situation. If you have limitation in the access, at that point you will need to put a device in the access node that is doing this conversion for your user. That's the other possibility. If you are not doing that, it's not going to work. If the problem is the access link speed, It's not going to work. The only other choice is to avoid having this user joining the communication. Is it clear? Anything else? Yes. The three different stream is the summation of the 3 bit rates. Here is the largest bit rate plus something for the coordination. That's the difference. So the yellow stream is almost the red one, plus something. Something for coordination, formatting things in such a way that you can extract the blue and the red. The other case, you add up the 3 bit rates because you send them independently. 3 or 4 or whatever the number of coding that you need. I don't understand. Say that again. Absolutely. If you need to support k different coding scheme, not in terms of different coding, but in different, for example, in terms of different set of parameters that the receiver is using, you need to generate these k flows independently. As I said, it's not as bad as in the case of multicast, which is scaling linearly this process with the number of receivers. This is only scaling linearly with the number of different coding or different bit rates that you want to support, which normally is limited. It's not more than a few units, okay? Typically much less than 10. But still, yeah, you have to generate the tree. So the bit rate you generate is the summation of the bit rates. The complexity increases by a factor of k, where k is the number of coders that you want. Yes? Yes, but this is exactly what is in this picture here. You generate the yellow, but then you need somewhere. I say that you typically do that here. You could do that in other point in the network, of course, but that requires even more support from the network. You can do the splitting and the extraction of a sublayer in any point in your path, whatever is more convenient. I'm simply stating that if you have to realize it, since typically there will be no provider doing that in its forwarding node, you need to act on some nodes with your device, and the easiest and the only point in which you typically can do that is when you are connected to the user, because you know this is known by the provider of this service. Okay, these access points are known. You know where are. Everything else within this cloud is completely unknown, so you don't know how to act. Okay? Of course, there are many other solutions, intermediate or hybrid solutions. You can have some servers that you deploy, okay, yet you deploy in different points in your network. You generate the signal here, you distribute to the server, and then the server will take care of generating the proper coding depending on the set of users that they have to select. So that's making the system scalable from another perspective. So there are many solutions. From the coding point of view, the idea of layering is the ability of extracting by receiving only part of this information, extracting something which is a proper layer, a proper something that I can reproduce in an efficient way, of course, with a reduced quality. Okay, which is not normally possible if you simply take the full stream and you drop some packets. That will not work. Okay. Any further question? Okay, let's have a break.